Okay, so this is the second video on, oh, I'm sorry, the second video lesson on sound, which will be about the properties of sound. In this lesson, we're going to be describing the pitch and volume of sound, describing pitch and volume as properties of sound in order to interpret and describe the properties of a sound wave representation. So in the previous lesson, we talked about how sound is a mechanical wave, which means it moves through a medium, that it travels fastest through the most dense mediums just because of how it is. It is basically a mechanical wave that needs to pass through things, so the more closely packed together things are, the faster it's going to move through it. And we also said that it's a longitudinal wave. So at this point, we're going to talk about the properties of that wave. How do we measure how loud a pitch is, or how loud a sound is, I should say, or how high the pitch is? What do they look like in terms of the amplitude and frequency? How do they relate to the properties of waves we talked about last week? So some of this stuff might look familiar. Some of it will look a little bit different, but in general, this is all still talking about sound waves, which are energy. And here we go. So what are the properties of a sound wave? In your guided notes right now, you're going to be working on the pitch and frequency column. We're going to be jumping back and forth. We're going to start with pitch and frequency, and then we'll go to loudness and amplitude, and then speed of sound. So spoiler alert, pitch and frequency are the same thing. So what is pitch? You say, oh, that person's very pitchy, or they have a great pitch. Their pitch is perfect. Pitch is how high or how low a sound is. To demonstrate how high or how low a sound is. That is pitch. If you were to notice between these instruments here, you have a violin, which is very similar, but at the same time smaller than a cello, a trombone, and a flute, which are both wind instruments, but one's much larger than the other. And if you know anything about your orchestra instruments, the cello and the trombone are both much lower than their counterparts. So even though a violin and a cello look the same in terms of their shape, one's much bigger. The cello produces a much lower pitch, and the violin produces a much higher pitch. Both nice. Cello's the best. I'm not at all biased, of course, because I'm a cellist, but it just really is the best. It's been scientifically proven. Pitch depends on the frequency of the wave. So what we hear as pitch is actually the frequency of the wave showing up for our ears. That's how our ears are interpreting the frequency of sound waves. And just as a quick refresher here, frequency is the measure of how often a wave is cycling per second. Or another way of saying it is how fast a wave is traveling through a certain specific point, how many waves per second. So you notice here the amplitude of these two waves here are similar, or exactly the same, but the frequency would be different, right? On the top is a higher frequency because there's literally more of these waves passing through a specific point. Say it's this point here per second, because this is a time graph here. You're going to have, let's see, it's starting from here, so it's going to be 1, 2, 3, and something like a half of a wave. So 3.5 waves in that first second. This would have, maybe it looks like a third of a wave per second. So if it's 3.5 cycles per second, the frequency would be that, 3.5 hertz. And in the bottom here, it would be about 1/3 of a hertz. So just to remind you, frequency is the number of waves that pass by a point each second. I just said it, but if you need to see it, there it is. So here's an interesting point. In electromagnetic waves, we usually show this as being a representation of the total energy levels, right? The total displacement of matter. But in a sound wave or in a longitudinal wave, we'd have to show it as going back and forth, back and forth, back and forth, which just doesn't look nice on a graph. So the way we actually represent them is still with what looks like a transverse wave. It is instead of whatever we had talked about with that, we're going to be using pressure instead. So as you see pressure spiking, you can imagine right here we have that compression zone. And as you see the pressure now going the opposite way, this would be like a rarefaction. So you get compression, rarefaction, compression, rarefaction. So usually we've shown this as like a bunch of matter pushed together here and matter being spread out here. But it's much easier to interpret and say, oh yeah, the frequency of that wave would be blah, 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 or the amplitude would be like this if we look at it this way. So just so you know, we didn't just do a switcheroo there. It's just the way that we represent it to make it more easy to understand. So imagine that at the tops here we have compressions and here are rarefactions, even though they don't look the same as we showed before. A high frequency wave would just be one that you could even think of it as having more squigglies, right? That's just more times per second that it's cycling back and forth between compression to rarefaction. Okay. So if we were to think that this box represents, 1 second, this would have 3 waves up and down to here, 2, 3, and maybe a 3 1/4 waves per second. This one would have 6 and this one would have 13. So if this were sound, this would sound twice as high pitched as this did, and this would sound more than 4 times as high pitched as this does. But the way it actually sounds to our ears, it doesn't quite work that way. It would be nice if that was the case. But the way that our ears process sound is much different than that. That's a spoiler alert for next time. So the amplitude is the same, but the pitch changes. That would be like if somebody was singing at a low voice, low, it's not any louder because the volume or the amplitude isn't not changing, but the pitch does. So low frequency, low pitch. Medium frequency, medium pitch, and high frequency would have a high pitch. So I can't play this on here for you to hear. In fact, if you have a good pair of headphones, I would encourage you to go into the slides now and turn this on. I'm going to keep the volume low. You can turn it up a little bit at first. This isn't about amplitude here, it's about the frequency. Basically, humans can hear anything from 20 cycles per second all the way up to 20,000 cycles per second. And it's not that your ears are actually picking up those things and digitizing them, but there's little sensitive cells inside of your ears that will be able to understand it. And once again, that'll be in lesson 3 that we talk about that. So since pitch is really frequency, we measure pitch in hertz. This should be capitalized here because it was named after a man named Hertz who worked with sound. Humans can hear from anything from 20 hertz to 20,000 hertz. As you get older, you keep losing your range, usually from the high end down. You don't usually use your lower range, though you can certainly lose your hearing a number of different ways, just as you get older. Over 20,000 hertz, some animals are adapted to hear that. Below 20 hertz, you have some other animals that can hear that, like elephants. These will tend to travel much greater distances because there's less energy in them, and these would travel much much shorter distances because there's so much energy in it. It's most likely going to interact with something and get absorbed by the thing. But humans, 20 to 20,000. If you're just curious about other species, dogs seem to have, I'm just going to let you take a second to look at this, right? Okay, imagine you just took a look at this. Dogs have probably some of the greatest range, surprisingly dolphins even more than that. And you say, well, dolphins are underwater, how can they hear so well? Remember, underwater, liquid is a much better medium for sound because it's much more dense than air is. So dolphins can not only hear better, but they can also hear a lot more from much farther away. The sound travels faster through water without losing as much energy in the process. So interesting stuff here. Some are just adapted to smaller ranges. Some have high ranges only. Some have lower ranges to medium ranges, all for their particular environments. Mostly, what are they going to try to use it for that'll get them food or ensure their survival? So, if you think about the size of the instrument as affecting the pitch, what else could it necessarily affect? Would you think about the Higher frequency sound also representing a higher loudness level. Loudness doesn't necessarily affect the pitch, just like we said before with the amplitude. Now, a lot of people mess this up on, I say mess it up, but just didn't understand this when we were looking at the PHET simulation last week. When you change the amplitude of a sound or of a wave, it does not actually affect the frequency of it. Case in point, I can have a loud sound that is at the same exact frequency or pitch as another sound. So think about if I'm saying hi or hi, it's the same pitch, different amounts of loudness. So then what is loudness? How do we measure that? And the key is amplitude. Amplitude will change how loud something sounds. And that should make sense, because if the amplitude represents how much matter is being compressed or how much pressure you have in a wave, either pressure being this way or that way, you have a louder sound. That's basically how our ears have adapted to hear more basically energy moving through matter. So a softer sound could be lower pitched and softer, or higher pitched and softer. But the thing that would be changing as it's softer is it would have less matter being compressed in that time. And just a quick toss back to energy in a wave. The highest energy waves are the ones that have the highest frequency and the highest amplitude, going up and down a lot and going up and down greatly, compared to the least energy would be a wave that has very, very low frequency and low amplitude. So that would be low and soft, doesn't have nearly as much energy. So it measures how well a sound can be heard when we're talking about loudness. But to use the proper term, we talk about amplitude. So just two comparative waves that have the same exact frequency here. The lighter blue wave has a greater amplitude, meaning there's probably more matter being compressed, whether that's air or any kind of matter. But it would sound exactly the same pitch. So you say that wave height is one way of saying this. Energy in that is just more. Remember, this is what we're actually talking about. Not even a coiled spring, but lots of matter being compressed together with higher pressures and then rarefacted apart. If we were to take a look at what this might look like from a molecule point of view, say each of these dots represented a couple billion molecules. That's not even close to how small these things really are. But if you have a speaker with lower amplitude, it means that you wouldn't be compressing as much of the air in that area, right? And this isn't the greatest visual, because really the amount of air here would be the same, right? You'd have just more air in the rarefaction area that wasn't as spread out. But in a higher amplitude wave, it's like the speaker is pushing harder into it. If you'd imagine, like throwing a rock hard into water as opposed to dropping it into water, the harder the rock is thrown, the higher the waves are going to be, the more you're compressing, right? So that's the same idea with sound. We measure pitch and frequency in hertz, but we measure loudness in decibels. It's a very, very weird. It's a weird unit. It's not named after anybody. Oh, it is actually kind of named after Bell, who was the inventor of the telephone. It was a way of measuring the amount of energy loss over phone lines back in the day, so that people knew how much to boost the signal. To make sure that if you're calling somebody in Chicago back in the 19 whatevers, they would be able to hear you loud and clear instead of a little wispy voice because you're just so far away. It's a kind of a complicated unit, so I'm actually going to wait to start this up until the second lesson, and I'm going to pause the video right here.